are, they always hire UTEP students, and this year they haven't got one, and they're really upset because they've had good experiences. So the project is a summer internship for any student from UTEP, graduate students included, and the project is to work on a virtual patient project.
It's just grad students?
No, it includes graduate students.
It includes graduates, yeah.
So the virtual patient project takes the advanced virtual human technology and applies it to the medical domain to create interactive engaging characters, and so on and so forth. And if you know Java or C++, and Windows, a little bit of AI, machine learning, natural language graphics, AI, you don't have to know all of those things, but enough to be useful to them. Come see David or me, and we'll set you up.
And this is like the coolest project on Earth. So, and it's right in Marina Del Rey, in Los Angeles, and it's just a really great experience. I don't know if everybody remembers Joaquin Aguilar, who was graduated from the program a few years ago, but he spent last summer there.
And so did Nicole Whitman.
And Nicole Whitman, that's right. So, so they just had a great time.
3 miles from the beach.
If that.
Yeah. Do you want to introduce?
Also, I want to introduce Pietro Nicolai,
who is visiting us the next 6 months from Torre, Italy. A speaker the week before vacation. Fulvio Riso was his advisor. It was hoped that we were going to be here at the same time, but he arrived 4 days after Fulvio went back to took off. In any case, just so you see him in the hallway, you know who he is. He's participating in the robust and secure distributed systems group.
Welcome.
Thank you. Okay, so I'd like to welcome our speaker, Will Enriquez. I think it's okay to still call him Will.
Yeah, no, I still use it.
And since he's in Japan, he got his names backwards. This is Will's first name. It happens to all of us who spend time in Japan. So Will is actually a UTEP graduate, Bachelor of Science in Computer Science 2005. After his bachelor's, he won a very prestigious Mombusho scholarship, and he spent a year learning the language and sort of getting into the culture. And he recently completed his master's degree in applied physics. In Japan, the names of the research labs and the names of the research and the topics and the titles and the department, it's all mixed up. But he's really still doing computer science. We owe him a big debt because even today, when we're revising Raphael's master's thesis, we're looking at the conversations that you collected for us.
Oh, really? Wow.
Yes. So at one point, Tasha had a baby, sort of faster than expected, and we'll continue to work and gather the data for us, and that data we're still using.
Good.
So this will be just a short presentation, 15 or 20 minutes, but if you have questions, we'll hang around to answer them.
Okay, so I'm going to present my research. It's actually a slightly old research. This was the bulk of my master's work, and it's entitled Wireless Sensor Network-Based Navigation for Human-Aware Guidance Robot. And this was actually presented a couple of weeks ago, even though it was 2009, presented at Robio 2008. And this is a funny little thing just because it was held in Thailand and there was some problems at the airport and a little protest. And so it got postponed until just a couple of weeks ago. And so I just basically sort of reworked the slide. And so just as a quick flow, just to give a little bit of background, a little bit about the wireless sensor network, in case those of you that aren't familiar with wireless sensor networks. Then the field navigation concept using these network, the human awareness section, and the experiments, and then just some conclusions. So, the act of guidance is something that we do every day in our regular lives. So, a good example is museums. The guide will take you around from exhibit to exhibit, show you around different interesting points. Or also restaurants. When you first enter a restaurant, what do they call them? Hostesses or hosts?
Maitre d'?
Maitre d'. Well, I don't have that kind of money. They'll show you to your table. And you don't think about it, but this is actually a very common and very important form of guidance. So, in terms of using wireless sensor networks for research, there's been research in the past, but they use them sort of like beacons. And so basically, there's a sensor right there. I can move to that sensor, then to the next sensor, to the next sensor. And this is very useful, but only if you want to go to that particular beacon. And so I wanted to extend this idea, but a little bit differently. And then, of course, in terms of guidance robots, there's a very famous robot, it's a little bit old, but a very famous robot called Minerva. And Minerva was actually more focused on navigation than on guidance. And so even though it successfully gave tours around a museum, it never watched the human. And so if the robot went off in this direction giving the guidance, and me, as the patron, if I decided, well, I want to walk this way, Minerva doesn't care, Minerva keeps going. And so my question, this brought up two questions, and how can we use wireless sensor networks more effectively for robot guidance? And more importantly, what is this idea of what's the difference between guidance and simultaneous navigation? Meaning me and the robot just happen to be going in the same direction. So, for those of you that aren't familiar, this is a wireless sensor node from a wireless sensor network. And in particular, I use a brand called Crossbow. And they also go by the name Zigbee. I don't know, maybe the name might be something. And so as you can see, they're very small, about this big. And the best way to imagine them is if you take a small microprocessor and slap it onto a wireless network hub. Okay, and so these hubs, they all connect to each other. And the upside is that it's ad hoc, which means I just flip all these switches on and boom, the network just connects itself. I don't have to do any network programming, which is good because I'm horrible at network programming. And so this also gives you scalability. So if I want to increase the area in which my robot is navigating, I just buy more nodes and just turn them on. Now the downside is, just like with any other radio navigation system, you have inconsistent signal strengths. And this is due to attenuation or interference, people moving around in the area, it doesn't go through walls, this type of thing. So we developed a filter. And basically what we did is we ran an experiment where we ran the robot in a straight line from about 7 meters to about less than a meter. And we just collected raw signal strength. And so this is a graph showing this data coming in from a typical example. Now as you can see, this data is all over the place. I mean, you can't use this like this for navigation. So what we did is we created a filter that basically takes the deviation, meaning how different the values are from each other, over, I think, usually like 10 values. And so we check to see how different these 10 values are from each other. And once we have a baseline, we create a threshold, which we developed kind of through experimentation, just testing what was a good threshold. And when we have values that are outside of a certain threshold, meaning values that are very different from this previous 10, we just throw it away. And so this is different from smoothing algorithms, because smoothing algorithms will just bound you in. But what this does is it just ignores what we determine to be incorrect data. And so this yellow line now is an example of this filtered data for the exact same data set. And you can see it's still not perfect, but it's far better than it used to be. And this light blue line is a line that we built off the the ideal curve. This is basically, sorry, I can't remember the name. This is the ideal line that if the radio frequencies were perfect, this is what the line would look like. But of course, it's not a perfect world. But you can see that one thing we definitely determined is that it's far closer to the ideal line than the chaotic signals we were getting before. So in comparison, we also did just a basic average, and that's this dark purple line. And you can see that it's really nice and smooth because it's just a running average, but it doesn't follow this curve that we really need. And down here, you'll see that this is the error from our filter, using our filter, the signal strength, and this is the running average error. And of course, predictably, it compounds because as you keep going, the error just keeps getting added in and added in. So now, using these signal strengths, we construct what we call the field. Okay, and basically, what you can think, the best way to picture this, maybe just looking at the picture you can understand, but the best way to picture this is you're in a city that you've never been to. And you start walking, you know the building you want to go to, and you start walking around, you ask people, oh, where's the post office? And they say, oh, well, I don't really know, but I think it's in this direction. So you start moving in that direction. You find somebody else, oh, where's the post office? And they're, I don't really know, but I think it's in this direction. You start to compile all these different directions that are being suggested to you, and eventually you'll end up at your goal. Now, the nice thing about this is that we can aim this around major structures like walls. And so now our wireless sensor nodes are no longer flag posts. Meaning if I make the goal here, I just point like here, I just point everything to where I want the robot to go. And so in this way, I don't need to have a node right where I want it to be. I just have to point everything in the field towards it. In order to calculate this field, I place the nodes myself, but I use a very simple algorithm, which maybe somebody knows, is ray tracing, to determine whether or not the robot could potentially run into a wall if it follows the particular straight line. So like for instance here, even though this is the straight line to the goal, if the robot moves in this direction, it's going to run into this wall. And so in order to be able to point around automatically, we use ray tracing to calculate these angles. Then finally, taking these angles, we do this very, I don't even know why I was asked to put it in a formula. I think I could just explain it very simply with words, but you know, they like to see formulas. So basically what we do is we sort the incoming signal strengths from all the nodes we can read. Because sometimes you can't read them. Sometimes there's interference or it's behind a wall or what have you. And so we just take all these values into a list and we sort them based from biggest to smallest. And then if the goal or the area nearest the node nearest the goal is in the top list, then we take the next two. And if it's not, then we just take the strongest two. I don't know if that was confusing. Sorry. But basically we just look at the strongest two nodes in order to move towards the goal. For the human awareness section, what we did is we mounted a camera, but this camera doesn't look forward like most cameras on robots. It points backwards. And so this is actually watching the human as I'm following my robot. Okay, and what we do is we use a very simple algorithm called cam shift. And cam shift allows you to track usually a color or something within a frame. And we use it specifically to track the color of the shirt. And what we do is we take an initial image, and so this red box shows this color, which is inside the yellow, which is red, my shirt here. And it tracks the size of this box. And we compare it to later on in the experiment, where you can see the box, because I'm further away, is now much smaller. And so in comparing this ratio, I determine what behavior the robot should follow. And so the robot either guides normally when it feels that you're close enough. If it feels you've gone a little bit far away, it'll stop and say, follow me. And if you go really far away, it'll actually chase you to try to reestablish this appropriate distance.
But if you run up a stairway, you're safe, right?
It doesn't climb stairs yet, but maybe someday. And so in order to determine these behaviors and these actual distances, I actually ran an experiment with an experienced waitress. And what we did is we ran her in several scenarios, multiple versions of the same scenarios. We only told her that we were building a robot waiter. And so she didn't really know what exactly we were looking for. Really all I was concerned with was this distance. And so we would have her guide this customer through the restaurant, and she would say, she'd be guiding them to a table, and then, like for instance here, he's pulling out his cell phone. And as you can see, sort of, she stops and she like turns to when she realizes, oh, he's no longer following me. And so what I did is I measured these distances in the image, and I use these to create ratios. Because my vision system doesn't give me a distance. It doesn't say the human is 5 feet away. It just says the human is kind of far or kind of close. And so I wanted to compare those ratios with these ratios. And I came up with these values. And so it's, as you can see, it's not an exact distance, of course, because these are humans. And so it's just kind of, maybe this is a good distance, maybe this isn't. And that's what the robot tries to model. For the experiment, we used a robot called Chemupo. And it's actually, it's kind of shiny. This is actually a Pioneer 3 base. And I basically just built the top section, which is really just a computer sitting on top of this base. And it actually looks much nicer. I should have put the new pictures. But and so basically, here you can see the camera, which is pointing backwards. We have a touch screen, which gives us a map of the room that you're looking at. And you can basically click in the map of where you'd like to go. And you'll see, I'll have video, you'll see in a little bit. And then here on the front, I don't think you can see with the lights on, but here on the front is mounted is one of the network nodes. So not only are these wireless sensors spread out throughout the room, there's also one on the robot, so the robot can read and interact with the network. For the experiment area, I wanted to run it in an actual hallway, but for logistic purposes and danger purposes, this was just not feasible. And so basically I measured the hallway in our building, and I aligned tables to match this size. And so basically the idea here is that this is a doorway, and this is the goal. And so the robot should come this way and guide normally to here. But in some experiments, the human will actually make a wrong turn and go this way. And so when it goes the wrong way, it's a long enough distance for the robot to stop and actually chase after it. And so I have a few videos that are not very good, but this is the interface. And this is an older version, so you can't, here I only click on nodes, but it's the same basic idea. And so this is a kind of an initialization period. Okay, and so in this video, the robot is actually sitting right here. And so this bar is showing the direction that the field is suggesting that the robot should go. So if I'm here, right now the robot should go up to come into this target. And if it's here, I should move in this direction. And if I'm here, then I should move in this direction. And so this is just showing the direction that the robot would ultimately calculate. And now in newer versions, I only have this older video, but in the newer versions, you can click anywhere within this box, and the system will automatically calculate the direction to that point. Okay, and this is an example of the robot running. Unfortunately, it's at 4 times speed. And I get a lot of comments, why is the robot moving so slowly? But this is because the camera needs to be very slow, which is a problem that we've tried to deal with. But basically, if the robot turns too quickly, the camera loses you, and it thinks that you've left, when really it's just that the robot turned too quickly. But this is an example of me just going straight to the goal. And the robot looks much nicer now. I'm actually a little embarrassed to show this version, but this was the version that I went with at the time. So. And then it just stops. And actually, the important thing to notice here, though, is that the robot has no collision detection. Meaning, if I told it to run into the wall, it'll just go headlong right into the wall without even thinking about it. So this navigation that you've seen, this nice turning the curve, this is 100% done using the wireless sensor network field navigation system. So to answer the questions that we originally posed, how can we use these wireless sensors more effectively? And so we feel that by developing this field system, not only can we navigate to these nodes, but we can navigate to anywhere within the navigational space, which is an improvement on previous systems. And second, by testing and learning these appropriate distances that humans should maintain behind the wagers, we feel that this is actual guidance as opposed to just simultaneous navigation. And so for future work, we want to develop a dynamic filter. Right now, as I said earlier, I have to set this threshold through experimentation. But I'd like it to actually learn and feel from the field and actually adjust itself this threshold of what's an appropriate or what's an incorrect or correct value. Another idea is this map right now, I actually have to program it and build it myself, but we'd like it to be able to just kind of scan in architectural data and automatically produce not only the map, but where in the room these nodes should be placed. And then also, obviously, camera efficiency is a huge problem for this system right now. And so we're taking steps to improve it and build a new camera, faster servo, this type of system. And then, of course, more increased human-robot interaction. We'd actually like to do, because we can use the power of the network to not only navigate, but also for the robot to interact with the environment. And so actually the main thing I'm working on right now is having the robot call an elevator before it arrives. And so by the time the robot rolls up to the elevator, the doors are open and waiting. And that's about it. If you have any questions, I'd be happy to answer. Yes?
Hi. I wasn't here for your whole talk.
Okay.
Okay.
You want me to start again?
Yeah, I had extended office hours, so I'm a little late. What do you use? What programming language do you use?
Okay. Part of the network interface section is done in Java. This is because the company that I purchased these network nodes from, their interfacing software is only in Java for some reason. So I just interface the Java with and then the robot itself is done in C++. And so I use Java to interface with, I think, using a socket.
And that doesn't, I would think that would cause some slowdown in terms of...
Well, the nodes are actually pumping out messages at 2 messages a second.
Oh, okay.
And because in this particular research, I only have 8 nodes, so it's actually not a problem at this point. But we have thought about obviously just, actually right now I'm trying to migrate the entire thing to Java, but it's not going so good. I might try doing it the other way, migrating it all to C++.
Yeah, I would think it'd be worse in performance.
Yeah, no, yeah. I was just experimenting to try it out. But.
There is just for your information, I have no idea whether it would be applicable, but there was a candidate for ECE who gave a presentation about a language which is meant for real-time computing, which certainly this is an example of.
Right.
And it deals with concurrency, and you can actually write at a pretty high level in terms of concurrency. It's from UC Irvine.
Okay.
Might be interesting.
Thank you.
So what happens if the two of the nodes are right behind a wall and the other nodes are farther away, the robot's up against the wall and it thinks it should go the wrong direction?
Right, so at this point, when I place nodes, it's based on my own knowledge. I'm looking at the map and I know where. So I would just try to avoid this type of situation in the placement. If even barring that, even if it did happen, the robot in this research will just run right into the wall. But recently I've acquired some scanning laser sensors, and so I'm going to play with the idea of, I think it's called coastal navigation. Actually Minerva uses coastal navigation, and so basically when it reaches a wall, if it has an idea that I should go in this way, but there's a wall, I'll just skirt the wall, and so that'll be the first approach. And of course I'll try various others, but at this point it'll just right into the wall.
Can you go to the graph you have with the error measurements? Please.
This one? Oh, this one?
Yeah, that one. So what's this raw signal error?
Okay, so this right here is the error of the values coming in, just this very chaotic purple line coming in and then averaged. In comparison to this ideal line, which is this, I think here it's black. I'm colorblind, I'm not sure.
Okay, so you're computing this just to show you do not know that, the error.
Well, it's the error when compared to an ideal curve. So it is, I guess I can see what your point is, that it's not an actual, it's an estimate of an error, or guess at an error.
Because if you know the error, then you can calibrate the signal before you do any filter.
Right, and so like I say, this ideal curve is based on I forget the formula exactly, but it's based on the initial value and the final value, and it basically just draws this decaying curve like perfectly to match those 2 points.
So basically, you don't know about the error.
You can't know until afterwards. Yeah.
Okay.
Yes. Which is why we couldn't use. I forgot, but yes, sorry.
Now your average curve on there, what's that? What were you averaging?
I was just averaging every single one that came in.
Oh, so it was continuous, not a sliding window.
We tried doing windows, but it didn't. I don't know. I didn't like it either. So
That didn't work
I don't
out.
have the data. I'm sorry for that. But
Okay.
we did try like averaging 10, averaging 20, and and even with this filter, we tried filtering 10, filtering 5, filtering 20, and it just in terms of the navigation, 10 seemed to be the best with the filter.
So, well, if you ran the same path over and over again, would you get different places for the spikes? Or
Yes, because the field itself is very delicate. Well, not very delicate, but it is dependent on people moving around.
okay, so you can't pre-program the path with the stated, if I'm here, I expected it to
Right.
But
But the nice thing about this is because the system kind of accepts this imperfection. And it actually just, I don't need to line up right on the dot if I'm doing guidance. If I can get you this close to your table, then we consider it a success.
So how did you determine robot orientation?
The pose is actually determined by the robot itself. It has its own internal compass.
Okay.
Yeah, it's not a great solution, but like I said, this was my master's, and so it was the one I was prepared to settle
Yes,
for.
if you have that, I believe it were. Otherwise, I was just trying to figure out how you just dealt with wheel slip over time.
And so actually, no, the robot has its own internal compass to deal with this. But even when we disabled the compass and we told it, oh, you're starting at 0, just turn and go whatever you want.
Mhm.
The wheel slippage was obviously a problem, but with the kind of generic or vagueness of the system, it actually still managed to reach the goal. Because as bad as wheel slippage is, for this kind of distance, it was almost non-existent. So, yes, sorry.
So the rover is trying to track the human, at least in this example, you showed us that from the front
Yes.
clothing. Right?
Yes.
What if you turn around completely? Then,
Right. So-
and if your clothing doesn't look anything like the front, if from that angle it doesn't look anything like
In this version of the research, the robot will think you've disappeared.
so it's not immune to
Right, no. The
transmission.
camshaft algorithm only is chasing the color.
It only works for one person too, I guess. You have a full family in the same color, you're just in trouble.
Right, yes. And so these are all...
The different sizes.
So right now, the experiment only runs with the one person in the environment, but these are all steps that we're taking to include into the future of, being able to tell the difference between people. And, if someone, even right now, if someone crosses in front of the person, it'll just start tracking that person instead.
Right.
And so we want to avoid these problems, obviously, but it's not yet. Sorry.
Okay, so what's your original motivation for this work?
So the reason, we see this being applicable, as I said, the main one was restaurants. But it could also be used in for instance, hospitals. There's a lot of times where, where's this room, where's that room? I just need to take you to the room.
So your
Basically, anytime you have just guidance being done, this system can be used.
okay, because it has one field of application that is huge.
Well, it's a guidance is...
They can't tell you what it is.
Oh, okay, I'm sorry.
I'm going to tell you,
Okay.
and that's huge.
Yes.
We have UAVs,
Oh,
right?
yeah.
And Air Force have put a lot of effort on those. FAA has done a lot of effort because they would like to get rid of pilots,
Right.
actually, by 2015, for those of you who fly. But they gave up this idea. And the thing that they are giving up this idea is because the UAVs, they have a major shortfall that is something called situation awareness. They crash into each other.
Right.
They crash into civilian airplanes, and so on and so forth. So that's why, because they know exactly what they need to go and whatever their mission and everything like that, but they are not ready to understand where they are. So that you have tons of research opportunities to be working exactly what you are doing. If you are aware of the human, right?
Yes.
But I think the buzzword for you is situation awareness. And if you keep moving this direction, I think you have a brilliant market in the US.
Thank you for that suggestion, because actually, these sensors were actually originally developed for use outdoors, for extended data collection on different things. They're not really designed for robot navigation, although they have properties that lend themselves to that. And so, in some of the other labs in my school, they actually have a version of this. It's not the same kind of system, but it's only developed for outdoors. And it's not like GPS, it's this kind of system that just broadcasts. And so actually maybe that could be used with what you're suggesting with the UAV. And so I'll definitely look into that. Thank you.
That's huge.
Yeah, thank you very much.
I wonder about applicability of this technique for the headsets in museums. Presently, there are schemes where there'll be, let's say, an infrared transponder by every painting, and you're in front of it, it sees it, and it knows you're in front of this painting. I'm wondering about placing these around the exhibit so that you have a general purpose location mechanism where you can hang the paintings and then program the system know that when you're in the area of this painting, you should play the audio for it.
Well, this is actually very similar to what they call active RFID.
Uh-huh.
And so there's actually, in terms of the radio itself, there's no difference between this and active RFID.
Mm-hmm.
The only difference is that this has an actual network running, meaning I can transmit packets, and because it actually has a microprocessor, it'll actually run a small program.
Well, all the the 14 megahertz RFIDs have processors in them too. They just don't tell you they're there.
Well, then they're actually wireless sensor networks and they don't realize it.
Yeah, except they have no power source.
Well, this actually has a power
I know, but RFID, all the devices, I have a whole bunch of the 14 megahertz ones downstairs, and those are field powered, and they have a processor on board, so you can exploit that too. But what I'm wondering about is would this be a practical approach to, or a competitive approach to making a flexible museum space, where where your audio guide would know what to play? Is this how you'd build it?
I could see, the 1 second that I'm thinking about it, I could actually see this being used, taking your idea, taking it a step further, instead of just a headset, perhaps a handheld, where you would say, oh, I really like this painting, and it could give you directions to a painting by the same author.
Yeah, that's nice too.
So that's actually, yeah.
Okay, so let me go one step further.
Okay, take that, yes.
That was our starting point in 1998. I worked in a project that was exactly doing this. And the problem is that you have two things distracting you. One is, this path, the guidance where you're going to go to. Another one are the exhibits.
Right.
So basically people do not follow the navigation instructions.
Well,
because you have two points of attention. So the solution we had at that time was to develop an augmented system, but still PDA based. Now that you have these goggles, that you have pretty much like a screen of a F18 or something like that, that may be something you can use straight away.
And the nice thing about the system is that there is no path plan. It's all done, real time. It just says this is the direction to move in.
Yeah, but you have the goals.
Right, and that's my point. So I think that it lends itself nicely where, if I have to follow this line, well, I kind of like that painting over there, but this is my line. If I walk over to that painting, my angle just adjusts itself in the headset.
Right, exactly. So you have the goals, and if you divert from the original plan,
right. The system doesn't care.
You adapt to it,
right.
And you come up with a new path, right? Right. So that's good.
Great.
Well, thank you.
Thanks for that.